Okay, welcome everyone to the last day. So we are live streaming out, so today we are live streaming in this morning. Aravind couldn't come, he broke his toe, unfortunately. And we debated and we thought we could run an experiment, see how it works. And
just one toe?
Sorry?
Just one toe?
Just one toe. You can ask Aravind how bad it is, but in any case, we are happy that we thought this topic was of interest to the workshop on rounding. So he will talk about dependent rounding, which he has pioneered in many ways. So can you hear us, Aravind?
Yeah, I can. Thank you.
All right. Let's thank Drew for helping set this up and get going.
Thank you, everybody. Thanks again to the organizers for inviting me, and sorry that I can't be there physically with you. So this is a biased survey on dependent rounding, and it's organized as follows. So as a sort of simple warm-up, we'll see, how when you sample without replacement, you already get good tail bounds. In fact, there's a sort of forgotten result of hefting that I'll remind you about. And then we will see three major topics, where the last topic will kind of come back to the second topic, which is rounding with just linear constraint. So as a warm-up, suppose we consider the following problem. You have a universe of n elements, and you want to sample k of them. The standard method is, sample each element independently with probability k over n. The nice thing is with independence, of course, you get a lot of tail bounds and correlations are nice and so on. But the other method that may be more useful in certain applications is to sample exactly k elements. So just sample k elements at random without replacement. So let xi and yi be the indicators respectively in these two methods for sampling element I. And suppose you look at a linear combination of the xi's, let's call that x, and the same linear combination y of the yi's. Let's say it's a non-negative linear combination. Now we all know that x has a Chernoff-like tail because it's a sum of independent random variables. What about the tail of y? Well, most of us also know about it, but there is this somewhat forgotten result of hefting, which is actually pretty strong, which says that. So if you have again this y is this non-negative linear combination of these dependent random variables yi. Then hefting actually shows that for any convex and continuous f, the expected value of fy is less than or equal to the corresponding value for x, right? Now, for instance, if you take little f of x to be an exponential function, then immediately you get Chernoff type bounds for y, because the classical Chernoff hefting bounds show that the exponential, the e of, so if you use f to be the exponential function, then that's what leads to the Chernoff hefting type tail bounds, right? So once again, most of us would know that in sampling without replacement, one gets Chernoff hefting type things, but actually hefting has this more general result. So what does it say? So one perspective on this is the following: is that the yi's satisfy the hard constraint that they add up to k with probability 1, right? And on the other hand, for example, from what we saw in the previous slide by hefting, we know that they enjoy good tail properties as well. So the motivating question for us really would be the following. Suppose we cannot do independent rounding under various circumstances. For instance, if we have to obey a hard constraint like being an independent set in a particular matroid, can we obey a few such structured constraints while still enjoying many of the benefits of independence, like concentration and correlation bounds, right? So this is the sort of motivating question for us. So that's just a simple warm-up. Now let me go to the first part of the talk. So this is some old work of mine from in retrospect, I was not aware of the work of Agiv and Spirit and Co. then, but really it's a randomized version of their very powerful pipe-edge rounding technique. So it takes the following form, right? So you're given a sum of, let's say, probabilities xi that add up, let's say, an integer L. This integrality is not very important, but yeah. So let's say they add up to an integer L. Then we want to round the little xi's to binary values capital Xi, such that the following three properties are true. The first is a natural marginal preservation property. uppercase xi should be 1 with probability lowercase xi. The second is that you need to preserve the sum with probability 1, like we saw in sampling without replacement. So with probability 1, the uppercase xi should add up to the lowercase xi's. And third, we want as strong a negative correlation property as we can. Right now, the following will suffice, and we'll look at more sophisticated ones later. This is technically called the negative cylinder property, or informally negative correlation, which is essentially that if you take any subset S of these bits, then the S of these random variables capital Xi, and take any bit B, the probability that all these Xi's equal B, as one can kind of informally express, is less than or equal to the product of the corresponding probabilities. So in probability, this is called the negative cylinder property, right? Informally, again, it's a form of negative correlation, right? So let's think about this problem. So you're given these little Xi's that add up to an integer L. The first property is natural. The second is, is already somewhat interesting. And the third, one sort of expects from the second property, although the third property doesn't follow from the second property. 2 doesn't always imply 3. But since these kind of balance each other by adding up to L with probability 1, you informally expect that they are sort of negatively dependent on each other. Now, so what that paper of mine did is it gave a randomized polynomial time algorithm to do this rounding with satisfying all these properties. Let's see an example. We'll see a basic example. So, by the way, once again, for some perspective about the 3 properties, preserving the marginals is of course natural, and the sum preservation is often very useful when you have simple hard constraints like the budget should be at most a certain value, the number of paths you need to route is at least this much, and so on. And negative cylinder already implies Chernoff bounds, not for arbitrary functions, but for non-negative combinations of the xi, right? So later again, we'll see that with more powerful negative dependence, we can expect more. Right now, we are looking only at non-negative linear combinations of the xi's, but more generally, we can ask for concentration of, arbitrary structured functions f of the xi's, and we'll look at those later. But right now, for these simple sums, there is some old work of Panconesi and myself, for instance, that shows that negative cylinder already implies Chernoff. Now, let's see a simple application of this. Although Chandra sent to me a couple of weeks ago some really nice recent work of his that simplifies this quite a bit. I'll talk about the work from my paper here. So it's the same classical Raghavan-Thompson low congestion routing problem, but now we have a multi-path routing problem, right? So you're given some pairs of vertices in a graph, S1, T1, S2, T2, etc. And for every SITI pair, and you're also for each SITI pair, let's say you're given a bundle PI of SITI paths. And among these, you need to choose RI paths separately for every SITI pair in order to minimize the maximum congestion on any edge. And as usual, the congestion on an edge is the number of routing paths that you choose that flow over that particular edge, and you want to do a min-max here, right? So this is the standard Raghavan-Thompson problem, and in their case, all the RIs are equal to 1, single path routing, and while here we want to do multipath routing. The point of this work is, as we'll see in the next slide, just by using this simple dependent rounding, you get in fact the exact same congestion bounds as does their classical work. So how does it work? Very easy. So write the standard LP for the problem. So suppose the bundle PI for the SITI pair has paths PI,1, PI,2, and so on. So that's the notation in the second line. So Pij is the jth path in the bundle P sub I. And we have a variable W for the congestion. And you want to minimize it subject to, for every pair I, choose exactly RI paths. And for every edge E, the total load on it is at most W. And the difference from integer multi-commodity flow is that every Xij has to be at most 1, right? So it can't be an arbitrary integer. The main difference from integer multi-commodity flow is that you really have to choose Ri distinct paths from the bundle Pi, right? That's the third constraint. That's what makes the problem interesting, right? So this is the natural LP. And now that we are on with dependent rounding, constraint number 1, notice that the constraints 1 are completely separable, right? So for every I, the variables involved in it are, for the different I's don't share variables here. So for every I, you can look at constraint 1 as an instance of dependent rounding. You are given these values little xij that add up to an integer ri. So we can round them using dependent rounding in order to get exactly ri of them to be 1. And we do this separately and independently for all the different i's, right? So if we do that, then constraint 1 is satisfied with probability 1. And what about constraint 2? Now the point is, if you take any particular edge and look at the left-hand side of constraint number 2, it becomes a sum of indicator random variables, but these indicators are either independent or negatively dependent on each other. So overall, the left-hand side of constraint number 2 for any particular edge E is a sum of really negative cylinder random variables, right? Therefore, we can apply Chernoff by this work of Panfanesi and myself. So you can just plug in the Chernoff bounds, although they're not independent. And now we just proceed just like in Raghavan-Thompson, right? So you look at the deviation above the LP value W, such that Chernoff will say that the probability of such a deviation above the mean W, the probability of it is, let's say, at most 1 over 2m, where m is the number of edges in the graph, and then just do a union bound over all the m edges in the graph, so that with probability at least half, you get a certain congestion value, which is the same as in Raghavan-Thompson, right? So it's a simple application of dependent rounding. So once again, when I developed it, I was not aware of Agib-Sviridенko. Quite a number of the original applications in the paper of mine follow from Agib-Sviridенko, but this one does not appear to, right? So it shows you the usefulness of, on the one hand, satisfying hard constraints like 1, and simultaneously having something like the negative dependence property, which for now would just be the simple negative cylinder property, which is sufficient to get Chernoff bounds as long as you're interested only in a sum of these random variables, right? So this is just a motivating application. By the way, how do you do this dependent rounding? So again, going back a little, so you're given these little xi's, and you want to round them to the uppercase xi's that satisfy these 3 properties, right? So how do you do it? It's actually very simple. Just round them gradually 2 at a time, handle them 2 at a time. So here is a simple idea. So again, here you're given these little xi's that add up to an integer L. As always, once you round an xi, once it hits 0 or 1, you don't modify it, and otherwise just do slow rounding. So how do you do it? You handle them 2 at a time. So take any 2 yet unrounded random variables like this xi, xj in this example. So currently they equal 0.7 and 0.4 respectively, right? The point is you need to preserve the sum, right? So now this 0.7 and 0.4 can be perturbed in 2 ways to preserve the sum, either as 1, 0.1 or 0.1, 1, right? And the nice thing is then you're making progress because you're rounding at least one coordinate. Now, the point is there are 2 choices. Just make the 2 choices with the appropriate probabilities so that the marginals don't change in expectation, that's all. So in this case, you can see that if you make the first choice with probability 2/3 and the second with probability 1/3, if you look at the first coordinate, 0.7, with probability 2/3 it becomes 1. With probability 1/3 it will become 0.1. So its expected value is the same as before, which is 0.7, and similarly for 0.4. Right? So there is a unique probability with which you can sort of make these 2 choices such that in expectation the value doesn't change. And once you have this, then by a straightforward induction, the marginals are preserved. That's easy. The negative cylinder correlation just takes a little more work, so it's also not very hard, right? So this is just the simple idea behind the paper. Basically, you gradually round them, and when any one variable hits 0 or 1, don't modify it, and otherwise take any 2 yet unrounded variables and simplify them probabilistically in one of 2 possible ways. That's all, right? And just keep repeating until you round everybody, right? So once again, this is really a randomized version of pi-page rounding, or to put it in the complementary fashion, pi-page rounding can be viewed as a de-randomization of such algorithms via the method of conditional probabilities. But as we'll see, the sort of probabilistic lens, over time, has led to interesting extensions just by, just like with the probabilistic method, in spirit, in principle, it reduces to counting, right? But we all know that just the probabilistic lens, lets us develop interesting applications and extensions, and we'll see some of them, right? So this is just basic dependent rounding. Was there a question?
No.
Okay. So now you just have one linear constraint. Now I'll move on to some very powerful work of Kalinescu, Chekuri, Paul, and Wodrak. which essentially boils down to our language a collection of pairwise disjoint constraints of this form, but with some additional wrinkles, right? So what they show is the following. So it's a very well-known result. What they show: want to maximize a monotone submodular function subject to either lying in a matroid or being a base of a matroid. In this case, of course, it will be a base of a matroid. Then the problem can be approximated to within 1 minus 1 over e, which is best possible. It generalizes a variety of earlier known results like max coverage and so on. Right? There are two parts to the paper. I'll go fast over the first part because it's not related to what we'll discuss here. The part one, by using some really elegant local search, essentially what they show is that there is a natural relaxation. One of the natural relaxations for a submodular function is what is called the multilinear extension, that can be approximated to an optimal value of 1 minus 1 over e. That's the first part. So let's just take that as a black box, right? So and then you can view their work is essentially using a dependent rounding carefully to round of part one. So, and in this part, there is no loss in expectation. Therefore, the total expected loss is just 1 minus 1 over e. Right? So let's forget about the objective function right now. So you're given a point x in the matroid base point. So this notation of n is the family of convex combinations of the indicators of all the bases of a matroid. Right? So how to round a point that is inside this polytope, right? Now, we are done if we are already at a vertex, and if we are not at a vertex, recall the very nice properties of the linear independence properties of the tight sets. So, for instance, you can see in the Lau Ravi Singh book that the following really nice property is true. So, suppose you have an arbitrary point, and you look at the tight constraints, and you take a linearly independent basis for them. Then, without loss of generality, you can assume that it's supported on disjoint sets. In other words, so for instance, if you look, you can always extract a linearly independent. You can always extract a basis for the tight constraints at the given point x, which are of this form. For instance, you have some number of variables that add up to 2, some number of other variables add up to 3, and so on. So these constraints are completely supported on, or have right-hand sides being integers, and they are supported on completely, disjoint sets basically. Okay, so essentially, once you have this, you can treat each of these separately. But of course, we are inside a polytope. We have to be careful. It's not as simple as in the earlier rounding, but the spirit is just the same. So let's let's focus on one of these constraints. Say this x6 plus x9, etc., adding up to 3. Right. So again, suppose you have xi and xj as part of this constraint, and suppose again they're 0.7 and 0.4. The difference now is you may not always be able to entirely round one of these variables to 1 or 0 right away, because you may create a new tight constraint while you perturb these, right? So, but of course, what is true still is that there are strictly positive epsilon and delta, such that you can either perturb the points, the 0.7, 0.4 by plus epsilon minus epsilon, or minus delta plus delta, such that you make progress, right? So such that either one of these coordinates hits 0 or 1, which is great, or one more linearly independent constraint becomes tight. So you're increasing the size of the basis, right? So of course you stop whichever happens first. And the point is, you still have these two distinct choices where epsilon and delta are strict, right? We don't have the luxury of maybe taking epsilon to be 0.3 and delta to be 0.6 like we had last time. Epsilon and delta could be smaller, but still, right? So now we just do the same as before, essentially the same as before, right? So you have two options for perturbing this pair, right? Perturb them with probabilities proportional to delta and epsilon, so that again the marginals don't change, right? So in the first move, 0.7 plus epsilon, 0.4 minus epsilon, make it with probability proportional to delta, and the second move, make it with probability proportional to epsilon. Therefore, again, of course, the expected change in any coordinate is 0, right? And one can use this to prove that just with with similar ideas as before, you can get the negative cylinder property. And the other key property that they use, which I did not mention so far, is that every one of these steps, none of them decreases the multilinear extension uppercase f of x in expectation, right? Therefore, in expectation, you lose nothing. Just keep conducting these steps, and of course, every one of these steps gives you progress, right? So this is a polynomial time algorithm because in each step you either round one more variable or you add to your linearly or to your basis of type sets. So of course, within a polynomial number of steps, you're done. Within a linear number of steps, you're done. So so this is a perspective one can have on the result, which is really using the structure of the tight sets in the matroid polytope. Essentially, you can sort of reduce the problem to something like pipage rounding or dependent rounding. Right? With the extra sort of complication that epsilon and delta may not be too large, but that's still okay. Right? So let's look at this. So let me summarize a part of what they do. It's not, of course, in this slide I'll summarize what they do, but it's only a part of what they do because I'm not talking about the submodular objective function. So in the language of dependent rounding, one can say that this is what they do, right? Given a point little x in a matroid base polytope or in a matroid polytope, you can round it in randomized polynomial time to an integer solution such that first of all the marginals are preserved, and second you get a matroid base with probability 1, right? So with probability 1, the rounded subset is indeed an independent set in your matroid. And third, you get the negative cylinder property, which is that once again, for any bit b and for every subset s of the coordinates, the probability that everybody in the subset takes on this value is at most the corresponding value for in the case of independent rounding. Right? So this is one perspective one can have on CCPV on part of their work. Without if we don't talk about the fact that they also handle the submodular objective, right? So one question one can ask is, okay, so we got the negative cylinder property here. Can one get even stronger negative dependence? As we'll see, this is not just a question of of some mathematical interest, but towards the very end, we'll see that the stronger the negative correlation, the better the concentration properties you can expect. So let's just abstractly ask this question for matroid. So given a point in a matroid polytope or in a matroid base polytope, can you round it to an independent set or a base of the matroid such that the marginals are preserved and such that you get even stronger negative dependence properties between the coordinates? That turns out to be possible. So earlier this year, there was this work of Perez, Singh and Bishnoi that I'll kind of summarize in one slide. There is an even stronger notion of negative correlation than cylinder negative association, and that's that's called negative association, and that says the following. So you have these x1 through xn, right? And suppose you have two functions f and g defined on subsets of these random variables, such that the two subsets are disjoint. So for example, f depends on x1, x5, and xx, and let's say g depends on x2, x7, and x9. So they're supported on disjoint subsets of the given random variables. And furthermore, let's say both are monotone increasing or both are monotone decreasing, right? And negative association is the property that for any such monotone f and g, the expected value of fg is less than or equal to the product of the two expectations, right? So x1 through xn are said to be negatively associated if for all monotone f and g supported on disjoint subsets, this negative dependence property is true. Okay, so this is a stronger notion than negative cylinder. Now note that, now for instance, the xi's need not be binary. So, and you immediately get tail bounds, for example, so if you look at the second bullet item, right, it talks about tail bounds, right? Now, the xi's need not be binary, so my work with Panconesi on tail bounds for the sum no longer hold if the xi's are non-binary. So suppose you have, let's say, a non-negative linear combination of the xi's, then since the exponential function is monotone, a very simple induction immediately tells you that the function that we care about in Chernoff type bounds, which is the left-hand side, the expected value of the product of e to the t ai xi, where t is some real number, by this negative, we immediately get this inequality. It's less than or equal to the product of the expectations, which of course makes calculations very simple, right? And again, negative cylinder doesn't hold here if the xi's are non-binary. Okay, so negative association, if you only are interested in sums, immediately gives you very quick tail bounds. By the way, it's a very powerful fact. I don't think it's used as much as probably it can be. For instance, there is some really nice work of Dubashi and Ranjan that says the following. It's a very useful fact. If you have m bins and you throw n balls independently but with arbitrary individual distributions into the bins, and you look at the vector of all the bin loads, right? So L1 is the number of balls that fell in bin 1, L2 is the number that fell in bin 2, and so on. Then this vector of random variables is actually negatively associated. In fact, I had the opportunity to use this in some work several years ago. So negative association is a very powerful property. And what Perez, Singh and Vishnoi show is that in fact, you can get a stronger version than what we saw in the previous slide. Let me go to the previous slide. In the previous slide, we got the CCPV rounding that gives negative cylinder. In fact, you get negative association. And they show that by using the Lovett-Maker random walk, let me not go into the details, you actually get negative association for matroid polytopes. So it's a very interesting, useful thing to keep in mind. And when I come to the very end, I'll kind of look at even further generalizations, even stronger negative association properties, and why they are useful in proving concentration bounds when you're interested in functions of the xi's that are not just sums. Okay, more structured functions, you can get significant tail bounds for. Okay, so please keep this in mind. I will now switch to the second part of the talk, which moves on to bipartite graphs and matroid intersection. Right? So far, we generally spoke that the primary thing we were interested in was a linear constraint or pairwise disjoint linear constraints. Let's make this setup a little more complicated now. So once again, there is this other work that I did, which in fact also is a randomized version of pi-page rounding. All right, so pi-page rounding was already powerful enough to capture a lot of these, but in deterministic language. Let me now just express it in probabilistic language. And soon after discussing it, you'll see what I say in the last line, which is that really the earlier dependent rounding that we saw is just what we see on this slide, but applied to a very simple star graph, basically. Okay, so a bipartite graph with just one vertex on one side. Right? So what's the rounding problem here? So now you're given a bipartite graph and you're given a value xij, let's say between 0 and 1 for every edge, otherwise just subtract the integer part. So what we want now is to round each little xij to uppercase xij, that is binary, in randomized polynomial time, such that once again the marginals are preserved, that's bullet number 1. And the second is the analog of preserving the sum. We now preserve the sum at every vertex, right? At every vertex, if you look at all the edges and count the sum of the capital Xij's, they add up to the small Xij's up to taking the floor or ceiling, right? So if the original sum was 4.7, the new sum will be 4 or 5, right? And then again, you want negative cylinder, but asking for negative cylinder for arbitrary subsets is impossible. So what we ask is that at every vertex, you look again at a vertex I, that's the third property. You look at the edges incident at that vertex, then that tuple of random variables corresponding to edges incident at I satisfy the negative cylinder property. Right? So once again, like I said, you can view this as a randomized version of pi-page rounding. But as we'll see in the very next slide, the probabilistic view is very helpful. Okay, and so a simple exercise is to observe that the very first dependent rounding we spoke about is actually just on what we see on the slide applied to a star graph. Okay, so I'll give you a moment to digest the slide. So once again, this is possible by a simple extension of the previous ideas in randomized polynomial time. Okay, but the probabilistic view is very helpful. And there's some very recent work from last year of Nikhil Bansal, Ola Svensson, and myself on scheduling to minimize weighted completion time. So, which extends the negative correlation to certain types of guaranteed negative correlation. What do we mean here? So, once again, recall the basic setup with a bipartite graph G and a value little xij for every edge, right? So, what we show is that for certain types of these input instances, you can guarantee almost all the properties of GKPS of the previous slide, and furthermore, for every vertex J on the right-hand side, B, right? For every J in B, and for many pairs of edges, I1, J and I2, J that are incident at J, it is not just true. So now please look at the inequality. So in the earlier inequality in negative cylinder, you will not have the 1 minus zeta term, right? So think of zeta as say 0.1, right? So what this is saying is that the probability that these two edges are both selected is less than or equal to 0.9 times the product of the two probabilities. So in other words, you don't just have negative correlation, but a guaranteed amount of negative correlation in the form of the zeta, which is some tiny but positive constant, right? So, so once again, it's the probabilistic interpretation which kind of lends itself to extensions like this. And I won't go over the proof of this, but the sort of motivating application is to beat the well-known 3/2 approximation for a certain scheduling problem, which is to schedule on unrelated parallel machines to minimize weighted completion time. We could improve it by a small constant, and there's been further significant progress in work of Shi Li that you would have heard about earlier this week. So, what I wanted to mention is that GKPS can be used as a framework for some of these. Let me now show you in a little more detail another such application. This is for stochastic matching, and this is work of Bansal, Gupta, Lee, Mestre, Nagarajan, and Rudra. Okay, so in case you haven't seen stochastic matching, it's a very interesting variant of matching whose complexity is actually not understood. It's not known if this problem is in P or is NP hard. It's very interesting, and the best approximability, none of it is known. So it's a very interesting problem. Without going into the motivations, let me define the problem. So you're given a graph. Every edge has a non-negative weight and a probability P. That's the first bullet. Second, every vertex V has a non-negative integral patience, let's call it TV. And the stochasticity in the problem comes because every edge is present independently with the given known probability PE. But to detect if the edge is actually present, we have to explicitly probe for it. And the next bullet item is interesting. If we choose to probe for the edge E and actually it turns out to be present, then we have to add it to our matching. So we start with the empty matching, we incrementally add to it by probing edges. If you probe for a certain edge and if it happens to be present, you have to add it to your matching. And of course, then delete all the incident edges, right? And finally, where does the patience play a role? So at any vertex V, the incident edges can be probed at most TV times. The vertex V loses its patience beyond that time, right? So these are the constraints of the problem. And of course, what you want is a matching of maximum expected weight. So it boils down to in what order, maybe adaptively or non-adaptively, will you probe the edges in order to maximize the expected weight of the matching that you construct. And of course, when we say expected weight, we mean that the randomness is both over the stochasticity in the input and the algorithm's randomization. Okay, so this is the problem. I'll give you a moment to stare at the problem. And once again, it's very interesting. Its complexity is very much not understood yet for such a basic sounding problem. Even if you drop the patience constraint and so on, I don't think the complexity is known. Okay, so what these authors achieve is a 1/4 approximation for this for bipartite graphs. They get other results as well, and some of these results have been improved upon, but their algorithm can be very sort of succinctly described using dependent rounding. So I thought it would be a nice example to show you. Okay, so this is the problem, and they're going to focus on bipartite graphs. And once you have a bipartite graph, we can naturally run the dependent rounding that we just saw a couple of slides ago. So here is what we'll do. So let's first write the natural LP. By the way, the interesting thing is in this LP, you an integral random variable, integral variable, and relax it to a fractional one. But really, the LP naturally works with only fractional values. So the natural benchmark LP is the following. So imagine an optimal probing algorithm. It will probe edge E with some probability, right? The probability could be binary, but it could also be fractional. So let XE denote the sort of probing probability of an optimal algorithm, right? Then the constraints are more or less straightforward. And of course, I wrote the constraint 0 XE less than or equal to 1, not in this list, but towards the end, right? So this is, so if you stare at it, the first is the matching constraint, the second is the patience constraint, and subject to these, you want to maximize the expected weight of the matching that you construct. And you can easily see that this is a valid relaxation. So solve this LP to find an X, and now forget these constraints. And since the graph is bipartite, their algorithm will go ahead and run GKPS on X. Okay, so forget these constraints at this point. But have the constraints 5, right? The constraint family 5, those are precisely the constraints that are preserved with probability 1 by GKPS, right? So let me just go up like 2-3 slides.
So if you can I ask a question?
Yes, please.
So this doesn't seem to allow adaptive sampling, right?
So this is just a relaxation. It's just a relaxation.
But what if your decision to sample an edge depends on what you saw for previous edges?
Sure. Yeah. So this this LP, I'm not claiming that it's an optimal. All I'm claiming is it's a relaxation. That's a good point. Yeah. So I mean, how to model adaptivity? All that is very interesting. Yeah. What's the power of adaptivity versus non-adaptivity? Those are very interesting questions. Yeah. I just this is a valid relaxation because in the objective, PEXE is the probability that you probe XE and that the edge is present, right? In which case, since you're forced to put the edge in your matching, the objective is indeed, the term in line number 3 is indeed indeed a relaxation for the expected value. Yeah. Thank you. So once again now, so the algorithm is going to be, their algorithm is you solve this relaxation and forget these constraints and just run GKPS on this vector little x. And if I go a few slides up, look at the second sum preservation constraint. So the sum is preserved at every vertex, right, up to floor or ceiling. So with probability 1. So coming back to our slide, right? Coming back to our slide, if you run GKPS, then the constraints in 5 will be satisfied with probability 1, right? So what GKPS will give you is a subset of edges that satisfy 5 with probability 1, right? So you don't need to worry about violating the patience of a vertex. And now what they do is, once you get this subset of edges, probe them in random order, basically. And with some amount of analysis where the negative correlation is important, they prove that finally the probability that edge E is probed is at least X, and that gives you the 4 approximation. Okay. So I haven't given you really any proof, but just to give you a simple idea of how these kinds of dependent rounding frameworks can be used. Yeah, please do stop me if you have questions. So what about further? How much can we go beyond this GKPS kind of thing? There is, one such significant work of Chekuri, Wondrak, and Zinklusen which goes significantly beyond. And there is a really nice parameter gamma here that I'd like you to sort of keep in mind. Okay, so they show a few different results, in particular for non-bipartite matching, etc. also. But I'll only focus on matroid intersection. One of the results they show is the following. So suppose you're given 2 matroids over the same ground set. You have a point XE that lies in the polytope of both matroids. In other words, it lies in the matroid intersection polytope. They prove that any such point, and then you're given a parameter gamma that cannot be 0. Think of it as a small positive parameter. You can, this little x, you can round it to an uppercase x, right? Such that unfortunately you have to do scaling down. Think of gamma as 0.01. So you do have to scale down the E by this tiny value gamma. So you still get most of it, 1 minus gamma. And then what they show is that if you look at the second main, the main inequality in this page is that if you look at any non-negative linear combination of these uppercase x's, you get a Chernoff type bound. Right? Now, one can ask is, and by the way, in the Chernoff bound, notice that there is a gamma in the exponent, right? So if you look at the right-hand side of this large deviation bound, everything looks similar to Chernoff except that there is the gamma also in the exponent, right? One can ask whether gamma can be made 0. So one way to think about it is, you have a point in the perfect matching polytope of a bipartite graph. Can you round it to a perfect matching such that the perfect matching has sharp concentration for any any non-negative linear combination? That's unfortunately not true for arbitrary bipartite graphs and arbitrary weight functions. So that is why they have to shade it down a little bit by gamma, but then they get this very strong tail bound. Okay? one can ask if one can go beyond these. I'll come to that in the very last slide. Right? So one of my points was to bring up what is known for sharp concentration under a variety of rounding scenarios. Right? Sharp concentration is easy when you have independence or other such nice things. What, for example, this paper shows is that under these very challenging circumstances, one can still get very good tail bounds, but up to the small scaling down basically. So they use a swap rounding technique that they developed before, along with new martingale ideas in this paper. So this is the second part of the talk. So just to summarize, in the first part, we saw about a simple family of linear constraints and a more sophisticated setting where you have a matroid polytope and you have essentially you have a bunch of disjoint linear constraints. In the second part of the talk, we have seen rounding in bipartite problems and more generally for matroid intersection. Right? Now, I want to go back to the first problem, but make it significantly more complicated. Okay, so let's first handle an easy question. So the basic dependent rounding preserved the sum of thexi's, right, with probability 1. What if you want to preserve a weighted linear combination? That's easy actually, there's really nothing to do. Those are the first 3 bullet items. So, well, you need to maintain the weighted linear combination. So when you modify xi xj, just instead of doing plus epsilon minus epsilon, you just weight the plus epsilon by aj over ai, and similarly when you do the negative delta, you weight it by the same factor, that's all. And once again, you have these 2 options where epsilon and delta are strictly positive, and you take the first option with probability proportional to delta, the second with probability proportional to epsilon. Once again, marginal preservation and negative cylinder are easy to show. Now, one minor wrinkle is you may have to leave one variable finally unrounded, but that's usually not you can handle it in many different ways. So that's not a problem. So essentially this problem is easy. But let's make it, you have 2 significant complications, which are, what if the AIs are of mixed signs, right? Some AIs are positive, some are negative, right? Then, if you look at what the above does, so for instance, if AI and AJ are of opposite signs, clearly when the above procedure tries to round the pair xi xj, it will actually positively correlate them, right? Because if you want to preserve xi minus xj, you either have to increase both or decrease both, right? So you have to necessarily positively correlate them. So actually both these complications come up in certain facility location problems. Second, what if we, unlike in negative cylinder where we are only interested in E of x3, x5 or E of 1 minus x3 times 1 minus x5. So suppose you have mixed terms, as you see in the second bullet item at the bottom, which is, suppose you are interested in the probability that x3 is 1, x5 is 0, x8 is 1 and x10 is 0, right? So you have mixed terms. They're not all the same bit, but they could be a mixture of both the bits 0 and 1, right? So, without mentioning the facility location context, mention that it does appear in some recent work with my current and former students, David Harris, Tommy Pinsel and Kuat Trin, right? We develop a certain method called symmetric randomized dependent rounding to handle this. The most important keyword here is randomized, right? What do we mean by randomized? Because dependent rounding is already randomized, of course, right? So we'll see. Okay, so this is the problem we want to solve. Okay, so again, please look at the first line. You want to preserve the sum over all I of ai and xi, but now the AIs could be of mixed signs. And furthermore, you're interested in expected values like the one towards the bottom of the slide where you have x3 and x8, but also 1 minus x5 and 1 minus x2, right? So what do you do in such cases? So here is the simple intuition, and then I'll give you the algorithm. So some high-level ideas are as follows. The first is simple. You keep rounding gradually, and of course, once a variable is rounded to 0 or 1, don't touch it, right? And just like we saw before, you may have to leave some variables rounded. We will keep some constant number of variables unrounded, right? You think of this t as something like 1 over epsilon, where epsilon will be some error parameter, that's a small constant. So you leave like 1 over epsilon variables unrounded, where epsilon is a small constant, right? And how do we handle the case where AI and AJ are of opposite signs? Here is a natural idea. Once again, remember, we are only interested in the yet unrounded variables, right? So throw out everything that's been rounded to 0 or 1. Of the remaining unrounded variables, suppose there are 20 of them, just pick a pair at random, right? If you pick a pair at random, right, the probability of choosing an opposite sign pair is at most a half, right? And that will happen when they are balanced as 10-10, right? If there are 10 positive and 10 negative AIs, then if you pick a pair at random, then the probability that you pick of opposite signs is a half, basically, right? Otherwise, so with probability half at least, you'll pick the same a pair of same sign, which is very good for us, right? And also, we'll only make small moves, as we'll see. In the move by epsilon and delta, you won't move aggressively, but make small moves. And finally, actually, I don't know if this is really necessary, but it makes the analysis simple. We actually, essentially make epsilon and delta the same, right? So we make symmetric moves. But I think the most important ingredient is sort of proceeding randomly by picking an unrounded pair at random, right? So let's make this a little more precise now. So the algorithm is as follows. So once again, the first line you see that the vector x without loss of generality has all entries strictly between 0 and 1. And you have this weight vector A, which doesn't have any zeros. If there are zeros, then you can just round those coordinates independently. So you can assume without loss of generality that no AI is 0, but otherwise they can be of mixed signs. Now, let delta be a certain term, right? It's the minimum over all I. Essentially, this delta, the interesting thing that seems to make the analysis work, at least the way we analyze it, is to pick one global delta. So what do we normally do? We first pick normally you'll pick a pair I and j to modify, and once you pick I and j, that pair will suggest an epsilon and delta to perturb with, right? To perturb by. Instead, actually what turns out to work is to pick one global delta, which is the smallest by which you can perturb any variable. That is the minimum over all I of how much it can be varied by, multiplied by the magnitude of AI, and then second, pick a pair at random, basically, like I said, instead of an arbitrary pair, which is what all previous work does. Pick a random pair so that you have a decent chance of picking a same sign pair, and then update them symmetrically. With probability half, you move along EI minus EJ, weighted in some way, and with the remaining probability, you move in the opposite direction. The point is, you still make progress with decent probability, right? So one can easily prove that you make progress with probability at least omega of 1 over n, in the sense that the probability of rounding a variable in one step of this is at least omega of 1 over n, right? And it's easy to see that this preserves the marginals, and it also preserves the weighted sum, right? It preserves the weighted sum, because you move appropriately in the two different directions, EI and EJ, right? All that's easy to see, right? And we repeat this until at most t variables are left to be rounded, where t again think of it as a large constant. So this is the algorithm, basically.
So Aravind, quick question.
Yeah.
So, maybe I'm being silly, but can't you do the positive sum and negative sum separately, or that won't work?
So we tried that. At least our analysis seems to break down there. Yeah. So yeah, Chandra's point is, if you have these 20 variables where you have these 10 are positive and 10 are negative, why not simplify the 10 positives together and then the 10 negatives? It doesn't seem to, especially for the, so notice that we need guarantees of this form for expectations that are mixed like this, right? So it doesn't seem to help, but
So
I'm happy to talk to you offline in quotes. Okay, so furthermore, you want mixed terms like this. Okay? x3 times 1 minus x5 times x8 times 1 minus x10. Right? So here is the theorem. The theorem is a little hard to parse. So please, first of all, forget the second part of the theorem. Right? Just look at the first bullet item. What we show is the following. So if you have any two disjoint index sets S and T, right? The expected value of the xi, the product of the xi is all taken from S, times the product of the 1 minus xj is all taken from T, right? Ideally, you would have, what would be great is if you can get the right hand side without the exponent P, right? But that's too much to ask for, right? So instead what we get is exponent T. So notice, this exponent P, but notice that this P is like 1 minus epsilon. I mentioned that T is like 1 over epsilon. So this exponent P is like 1 minus epsilon, where we think of epsilon as a small constant, basically, right? This is what we get for an upper bound of this expectation. But we can also, the second item is, You also get a lower bound approximation, right? Now you get an exponent q which is larger than 1 necessarily, right? And the second bullet is a little hard to parse, so I'll just leave it like that, right? So so you get this, okay? Yeah. I think, as I was looking at this, so one of the answers to Chandra's question is, a partial answer to Chandra's question is, why not handle the positives separately and the negatives separately? Notice one interesting thing about this theorem: the magnitudes of the AIs play no part here, right? If you look at the exponents p and q have nothing to do with the magnitudes of the AIs themselves, right? So I think we tried the doing positives first and doing negatives second. Maybe we didn't do as good a job as we could have, but the exponents p and q there we got were dependent on the ratio of the maximum AI to the minimum AI kind of thing. So, but the results here you get, the exponents p and q have nothing to do with the magnitudes of the AIs themselves. So I think that's one partial answer to your question. At least in our analysis, we could not sort of eliminate the dependence on the sizes of these numbers, basically. While with this randomized algorithm, P and Q really are just like 1 minus epsilon or 1 plus epsilon, basically. Right? And how do you prove such a thing? I'll just give you a very simple idea. The sort of underlying. So once again, let's look at only the first bullet item. Right? You want to prove that you want to prove an upper bound on the expectation on the left-hand side. And remember that the algorithm does multiple rounding steps, right? Takes multiple small steps. We want to prove something for every step and then carry it through inductively, and that's the following, right? So please look at these 3 bullet items. The key point is that for the p that I mentioned in the for the exponent p that I mentioned in the last slide, the key thing is to show that our randomized algorithm in any one step does not. So please look at the first bullet item. There is an expected value of quantity that we are really interested in raised to the power of p, right? Right? The key theorem is to show that if you do one step of rounding as we do, then this quantity does not increase, right? So that's the key thing. Then that immediately implies by induction the second bullet item, which is that the expected value is the very end of, once again, a quantity that we think about power of p is less than or equal to what we started out with in the beginning, which is the right-hand side of the second bullet item, right? Right? So, and now finally, of course, what we care about is less than or equal to what we care about to the power of p, because what we care about lies between 0 and 1, right? So that's the third bullet. So combining the second and third bullet, is what we want. So the key property of any one step in our SRDR is to prove that this function, what we want raised to the p doesn't increase in expectation in any one step. Right? That's the heart of the thing. And similarly for the lower bound. For the lower bound, we show that something raised to the q doesn't decrease in expectation from one round. So to summarize this part, what we spoke about was to extend the first part of the talk by, if I go back a few slides, by saying, what if we want to preserve the sum of the AIXI at the very top, where the AIs could have mixed signs. And now, if you look at the very bottom, you want also mixed expectations, and in fact, not just upper bounds of these mixed expectations, but also lower bounds. In other words, what we want is almost independence. You want to round the xi's to such that AIXI is preserved up to keeping a constant number of variables finally unrounded, and such that finally the variables are essentially almost independent, right? They're not really almost independent, but they're something like they're almost k-wise independent. As k increases, the quality of the closeness to the independence decreases. But so essentially, this is like almost k-wise independence. Okay, where k can even be large, but then the quality of the approximation is weak. The quality of the distance to the independence is unfortunately high. Right? So this is the third part, and like I said, this naturally comes up in certain types of facility location problems that we worked on. I'll skip those details and conclude. By the way, the conclusion will also say why we care about some of these strong negative dependence properties, right? So anyway, the first conclusion is that these carefully introduced dependencies can be a very useful tool in dependent rounding. a very important question is, now as we saw from the work of Perez, Singh and Bishnoi, one can go beyond CCPV in getting even negative association for matroid polytopes. Now there is something even stronger called strong Rayleigh. Is that possible? Unfortunately, that's not possible for all matroids. That's actually true from a classical work of Seymour and Chandra, sorry, Seymour and Seymour's advisor. I'm sorry, excuse me that I'm blanking out. So, so from the 70s. So unfortunately, strong Rayleigh is not possible. Now, strong Rayleigh is strongly connected to analytical tools like real stable polynomials, which have seen lots of applications in our community. Now, let's look at the third bullet, right? Elhanan Mossel had this very interesting open question. So please look at the third bullet. Mossel's question was the following. So suppose you have x1 through xn that are negatively associated, not necessarily binary. Suppose you have an arbitrary function f of x1 through xn, but it's Lipschitz, right? It's Lipschitz. Can you get good tail bounds for that, right? Now recall that if x1 through xn are independent and f is Lipschitz, then by the classical Azuma mid-diarmid-like inequalities, you get strong tail bounds for f, right? If f is arbitrary but Lipschitz, you know that by mid-diarmid's inequality, you know that there are strong tail bounds, and these have had numerous applications in combinatorial optimization, right? Now, Mossel's conjecture was, in fact, suppose you unfortunately don't have independence, but suppose you have negative association. His conjecture is, in fact, that you get strong tails, like sub-Gaussian tails, for arbitrary Lipschitz functions. That's not known to be true yet. But what P. Mantle and Perez showed a couple of years ago is that, in fact, if the correlation is not just negative association, but something even stronger, which is the strong Rayleigh property, then in fact, one can get sub-Gaussian tails for arbitrary Lipschitz functions. Again, I think this result is perhaps not as well known in the theoretical computer science community as it should. It's a very powerful result. So one very interesting open question is, in general, when are negative association and the even stronger strong Rayleigh property possible in circumstances when you simply cannot have independence? I'll close with two specific questions. One is, like I said, in the Chekuri-Vondrack-Zenclusen setting, it'll be very interesting to see in what circumstances you can avoid the scaling down the 1 minus gamma. It's a very interesting open question. And finally, if you recall the guaranteed negative correlation from the work with Bansal and Svensson, right? We had it under certain specific circumstances. Can one give general conditions under which such things will hold? And I'll stop here. Thank you.
Questions? Okay, all right. Then let's thank Aravind, and you can ask him questions offline, send an email. Thank you, Aravind.
Thank you so much.
Nice break.